In this section, we are going to talk about the physiological responses to acute altitude exposure. Acute meaning short-term impact. What happens when we arrive at altitude? The first thing that will happen is that we'll start to hyperventilate. Our pulmonary ventilation increases almost immediately. And the reason for this is because, as we talked about in the previous section, the barometric pressure is reduced at altitude, which reduces the atmospheric partial pressure of oxygen, which in turn decreases the alveolar partial pressure of oxygen, how much oxygen in our alveoli or our lung. And this in turn causes a reduction of oxygen in the arterial blood being circulated in the systemic circulation. So this results in a low partial pressure of oxygen within the blood, and this is detected by the chemoreceptors in our aortic arch. The chemoreceptors send a sensory message, an afferent message to the CNS, and the CNS responds with an efferent message to increase ventilation. So this increased ventilation is accomplished by increasing both tidal volume and frequency. So tidal volume can be increased for several hours or days. And remember, minute ventilation is equal to frequency times tidal volume. So by increasing one or both of the factors, tidal volume or frequency, minute ventilation increases. When we increase minute ventilation, we start to hyperventilate, and this causes us to blow off too much CO2. And if you recall, in a different section, we talked about how CO2 content is an important regulator of pH, where if we have too much CO2 buildup, this causes acidosis and pH drops. If we have too little CO2, this causes us to become alkaline and pH increases. So in this case, we start to hyperventilate, we blow off too much CO2, we become alkaline, pH increases. So what we're going to talk about in this section is that the partial pressures of CO2 and O2 are a result of the low barometric pressure, and it's not a result of reduced function of the actual system. So this curve should look familiar. This is the hemoglobin oxygen dissociation curve, where the blue line is that baseline curve. And we talked about different factors which can shift the curve to the left or right. So at altitude, our body temperature drops, our pH increases because we're hyperventilating, and this causes a leftward shift of the curve. This means that we're going to have more binding of oxygen to hemoglobin at the lung in the loading portion, but at the tissue level, hemoglobin is going to bind more tightly to oxygen and give oxygen up less readily to myoglobin. So this results in less oxygen delivery at the tissue level. In addition, the kidneys will excrete more bicarbonate. And if you recall, we talked about how hydrogen ion combines with bicarbonate to create carbonic acid. Carbonic acid can then dissociate into water and CO2, and that CO2 is what we blow out at the mouth. So this has a hydrogen ion sparing effect, where if there's no bicarbonate for that hydrogen ion to bind to, then it inhibits us from getting rid of more CO2. So by the kidneys excreting bicarbonate, it helps us to keep the hydrogen ions in our body because it doesn't give the hydrogen ion an option to bind to it and then to be expelled from the body. So at rest, pulmonary diffusion is not limited by its ability to diffuse gas as far as dysfunction of the lung. The main factor is that low alveolar partial pressure that is a result of the low atmospheric partial pressure of oxygen. So hypoxemia or low oxygen content in the arterial blood is a direct reflection of low alveolar partial pressure of oxygen. At the same time, we have less oxygen being delivered to the muscles because of that leftward shift of the oxygen hemoglobin dissociation curve. We also talked about two other reasons why oxygen delivery is reduced. One being we have a decrease in blood flow because we're vasoconstricted. So less oxygen can be delivered to the muscles because of the reduced blood flow. And then the third being related to the reduction of the diffusion gradient of oxygen at the lung level and then also at the tissue level. So to talk about that a little bit more, we're going to use this figure. This figure should look familiar. The left-hand panel we've seen in a different section, where at sea level, the partial pressure of oxygen in the atmosphere is 159, where we just got this number by multiplying the barometric pressure by 21%. And then at the alveoli, the partial pressure of oxygen drops to 104 millimeters of mercury. And this drop is a result of us subtracting out the water vapor pressure. And then the 105 or 104 millimeter of mercury is going to drop to 100, and this is a result of the direct oxygen use of the lungs or the pulmonary system. So by the time the arterial blood is circulated through the systemic circulation, the partial pressure of oxygen is 100 millimeters of mercury. The partial pressure of oxygen leaving the tissues is 40, and this leaves us with a gradient of 60 millimeters of mercury, where we just subtract 100 minus 40. So let's take a look at altitude. At altitude, if we were to multiply the barometric pressure by 21%, we would get 96 millimeters of mercury. Subtract out water vapor pressure, and we would get 46 millimeters of mercury. Subtract out the oxygen going to supply the lung itself, and this leaves us with a partial pressure of oxygen of 42 millimeters of mercury. So the O2 content of the blood leaving the tissue is 27. So by subtracting 42 minus 27, we get a diffusion gradient of 15. So if you recall, if you think back to the Fick's law of diffusion, this law said that the rate of diffusion is going to be dependent upon three things. One being the surface area, the other being the thickness of the membrane, and the third being the diffusion gradient, the difference in the partial pressure. So according to Fick's law, the amount of oxygen that's going to be diffused across the tissue at altitude is going to be reduced because we have a reduction in this diffusion gradient. So in other words, at the tissue level, less oxygen is going to be delivered to the muscles because of a reduced oxygen gradient. So combined with the other factors of a leftward shift of the oxygen dissociation curve resulting in less oxygen delivery, and combined with the reduced blood flow because we're vasoconstricted, the end product is that less oxygen is going to be delivered to the muscle. And as a result, even though we're at rest or performing low intensity exercise, we are going to rely heavily on anaerobic metabolism because of these different factors. So the fact that this gradient is less or smaller at the tissue is critical because this has a direct impact on our exercise capacity, where less oxygen is going to be delivered to our mitochondria. So this is another figure of the hemoglobin dissociation curve, just illustrating the leftward shift of the curve, where more oxygen will be picked up by hemoglobin, but less oxygen will be delivered to the myoglobin at the tissue level. So other responses include a drop in plasma volume within a few hours. And this is caused by a few factors. One being since we're at altitude, The air is drier. Since we're hyperventilating, we're losing more insensible water loss through our respiratory tract. Also, as we vasoconstrict because we're cold, the venous return is going to increase to the heart. The atrial baroreceptors are going to detect this increase in pressure. And as a result, they're going to release ANP, atrial natriuretic peptide, which, if you recall, works in opposition or has opposite effects of aldosterone. So ANP is going to cause diuresis, and this is going to cause this is directly going to impact plasma volume, where plasma volume will be reduced. So we could lose up to 25% of our plasma volume. So this will result in a short-term increase in hematocrit, where if we take that column of blood and we reduce our plasma volume, our hematocrit has now relatively increased in relation to that total blood volume. However, our hematocrit itself has not yet increased. Our hematocrit will increase, but this takes about this takes weeks to months to occur. So the hypoxemia, or the low oxygen content in the blood, triggers erythropoietin release from the kidneys. And as you remember, this increases red blood cell production in the bone marrow and results in a long-term increase in hematocrit. So at altitude, our stroke volume, our maximal stroke volume, is going to be reduced because we have a reduction in plasma volume. Our maximum heart rate is going to be reduced due to a decrease in sympathetic nervous system response. So the overall impact is a reduction in maximal cardiac output. And if you recall, if you think back to the Fick's equation, where VO2 is equal to cardiac output times the AVO2 difference, so VO2 is equal to Q times the AVO difference. This is the reason why VO2 max decreases at altitude, because we have a reduction in both cardiac output, our maximal cardiac output, and we have a reduction in AVO2 difference due to that reduced oxygen diffusion gradient that we just talked about. We also have an increase in basal metabolic rate. This is due to T4 thyroxine. We also, our HPA axis may also be stressed, and our catecholamine secretion will also go up. So this means that our caloric expenditure at rest is increased at altitude. So we must increase the amount of calories or food we eat to maintain our body mass. And the calories should come mainly from carbohydrates, since we have shifted our reliance mainly on carbohydrates versus fat because we have less oxygen being delivered to the tissue level. So since we have this shift or heavy reliance on anaerobic metabolism, we would be led to believe that lactic acid would increase. However, what happens at altitude is lactic acid production decreases over time. And this is what we call the lactate paradox. Paradox meaning it goes against what we believe, it doesn't quite make sense, and we don't have an answer to explain this phenomenon. So this is the lactate paradox, where according to everything we just covered, and anaerobic metabolism would be heavily used, we believe lactic acid would increase. But what happens at altitude is that lactate production decreases over time. So this table summarizes everything we talked about, where it outlines the adaptations or physiological responses to altitude for each system. So for example, the pulmonary system, we talked about increased ventilation, and this happens through increased frequency and tidal volume. We talked about the leftward shift in the oxygen hemoglobin dissociation curve, and we talked about our pH increasing and we becoming more alkaline as a result of the low partial pressure being detected by our chemoreceptors, which then stimulate hyperventilation. At the heart, we have a decreased plasma volume due to the ANP stimulation and an increased respiratory water loss, and this causes a decrease in stroke volume. So heart rate at rest is going to be elevated. So don't worry about these 2 bullet points that are X'd out. The metabolic system is going to be affected by an increased metabolic rate and a decreased AVO2 difference. And this is due to the decreased partial pressure difference between arterial blood and venous blood. So as a result of a decreased oxygen delivery, we're going to rely more heavily on carbohydrates for energy. And then the lactate paradox states that lactic acid increases, but it eventually starts to decrease over time at altitude. Our kidneys help to maintain pH by excreting bicarbonate ions. So this helps to reduce pH levels, and it helps to conserve the amount of hydrogen ions in our body. It also increases red blood cell production by the kidneys' release of erythropoietin, and also the kidneys' diurese. And this is a result of ANP released from the heart, or the atrial. So at altitude, dehydration occurs faster because of our hyperventilation. So we're losing a lot more water through our respiratory tract. And this is insensible, so we don't sense this. Also, our kidneys are excreting more urine. And with sweating, we are going to become dehydrated quicker. But since the air is very dry at altitude, the sweat that we do sweat is going to be evaporated quickly. So we're not going to sense, or we're not going to be able to detect our actual sweat rate. So we won't be able to balance our hydration. So this is one of the reasons why dehydration occurs faster at altitude. Our appetite also declines at altitude, so paired this with an increase in metabolism, this could result in caloric deficit each day. So climbers and mountaineers need to be educated about eating and hydrating at altitude. And then maintenance of iron intake would also be important to support the increase in hematocrit. So Mount Everest, also known as Nepal in Siddharthma and in Tibet as Kwomalongma, is the Earth's highest mountain. So if we were to measure your VO2 max on Mount Everest, which falls off this chart, it would be probably about 30 to 40% of your actual VO2 max if it was measured at sea level. So Denver's mile high, and so you would expect your VO2 max to be a little bit lower in Denver when compared to sea level. And as we increase in altitude, for example, Pikes Peak, your VO2 max would be expected to be 70% of what it was measured at sea level. And then Mount Everest would be less than half of your VO2 max. So VO2 max drops dramatically as we ascend to altitude past 1,500 meters. And this is due to all of the factors that we've just covered, the cardiovascular, the metabolic, the renal, and the ventilation. So if you ever have a goal, or if you have a goal of hiking Mount Everest, the minimum sea level VO2 max that you must have is 50 mLs per kg per minute. And in this case, you should be able to climb the mountain without supplemental oxygen. So say if you measured your VO2 max at sea level, your VO2, and it was 62 mLs per kg per minute, at the top of Mount Everest, you could expect your VO2 max to be measured at 15 mLs per kg per minute, which at sea level, if this was your VO2 max, this would be equivalent to a cardiovascular patient, a patient with compromised cardiorespiratory function. So although your endurance performance would be drastically affected at altitude, your anaerobic performance may be unaffected, and then in some instances, it may even be enhanced. So for example, for a 100 or 400-meter track sprint, your anaerobic performance may not be different at altitude, but you might even have improved times due to less air resistance. So improved jump distances may also result. So high jump, long jump, throwing events will have varied effects, where maybe the discus will have a worsened effect due to the lack of air lift or lift caused by the air. The javelin may be increased or decreased as well. Okay, so this is the end of this section. So the data that I just showed you was based upon BMI, or body mass index. And using this data, we know that 33% of US adult women are obese and 28% of US adult men are obese. Obesity is more prevalent in African American women than Hispanic and Caucasians. So 25 to 40% of the variability in body fatness is attributed to genetics. This still leaves a great deal, 75%, is going to be determined by the environment. In this section, we're going to cover field-based methods of body composition, and the first method is anthropometry. We did anthropometry in Lab 1 in 354 lab, where we measured different circumferences, such as the hip and the waist. The anthropometric equations that are available use circumferences as predictors to estimate the body fatness of a person. And anthropometric measurements, specifically waist and hip circumferences, are the best way to measure body composition in the obese population. The assumptions of this measurement is that the circumferences are affected by fat mass, muscle mass, and skeletal mass, and therefore these measures are related to fat mass and lean body mass. So the circumferences are going to be the best way to measure body composition or estimate body composition in the obese population. It's also an easy way to measure weight loss or body fat loss in all populations if you don't have the body composition supplies and tools required for other field-based methods. So in males, if they have a waist circumference greater than 102 centimeters, this puts them at an increased risk for coronary heart disease and metabolic disease. Females with a waist circumference greater than 88 centimeters also have an increased risk for coronary heart disease and metabolic diseases. In lab, we also measured neck circumference, where this was related to sleep apnea, and the cutoffs are listed below, and were also listed in that first lab. Sagittal abdominal diameter is a measure of an anterior posterior thickness of the abdomen. So you would use a caliper that looked like this and place one side of the caliper at the umbilicus level and the other side posterior on the back of the person. And the width of the openness of the jaw would be measured, and this would be a measure of the sagittal abdominal diameter. So it's basically a depth measurement. This is strongly related to visceral adipose tissue in men and women, and it's also related to metabolic disease and cardiovascular disease risk. Body mass index is another field-based test that we did in Lab 1. It's also known as Quetelet's index. It's defined as weight in kilograms divided by height in meters squared. These cutoffs are something that you should know. If you're going to stay in this field, they will be very important for you to have at your disposal. So a BMI greater than 30 kilograms per meter square would classify an individual as obese. A BMI greater than 25 kilograms per meter squared would classify somebody as overweight. And an underweight BMI would be anything less than 18.5 kilograms per meter square. So to do this calculation, we've done this in class, but to review, what we do is take their weight, convert it to kilograms, and take their height, convert it to meters, and then plug and chug. So when we put in the numbers and calculate it, this person has a BMI of 24.2 kilograms per meter square, and this places them in a normal category. They are right on the cusp of being categorized as overweight, but in this case, they would still be classified as normal. Waist to hip ratio is another good measure of body composition, where we can classify somebody as having an android or pear-shaped body. An apple or android-shaped body is associated with excess fat around the abdomen, which is common in men. And there's a significant correlation with visceral fat in the abdomen with metabolic syndrome. Metabolic syndrome being a collection of diseases, including cardiovascular disease, type 2 diabetes, hypertension. Pear or gynoid-shaped bodies are pear-shaped where excess fat is carried around the thighs and the buttocks, and this is common in women. And this is not associated with an increased risk of metabolic syndrome. So these are the normative values for waist circumference and BMI. They're also listed in your ACSM guidelines book. For the test, you will be responsible for knowing the BMI cutoffs for underweight, normal, and overweight. You do not have to know the obesity classes. You just need to know that anything greater than 30 kilograms per meter squared is classified as obese. Again, the waist circumferences are something that you also need to know, where the cutoff for men is 102 centimeters and the cutoff for women is 88 centimeters. So if the waist circumference of a man or woman falls above the cutoff range, it increases their risk of coronary artery disease, metabolic syndrome, type 2 diabetes. So if you're placed in an overweight or obese category, this is associated with, as I mentioned earlier, an increased risk of cardiovascular disease, dyslipidemia, which means a dysregulation of lipids in the blood. So this is usually high triglycerides, high cholesterol, high LDL, and low HDL, LDL being the bad cholesterol and HDL being the good cholesterol. It's also associated with hypertension, glucose intolerance, which is type 2 diabetes, insulin resistance, diabetes, and cancer. Being classified as underweight is associated with fluid electrolyte imbalances, osteoporosis, and bone fractures, because remember, the way we build bone is by adding stress to that bone, and having a body weight that supports weight-bearing activities that stress the bone is going to increase bone mass density. On the other hand, if a person is underweight, not getting enough nutrients, this would result in osteoporosis and bone fractures. Being underweight is also associated with muscle wasting, cardiac arrhythmias. The cardiac arrhythmias are related to the fluid electrolyte imbalances in sodium, potassium, and calcium. Being underweight is also associated with sudden death, peripheral edema, reproductive and renal disorders. So there is a problem with BMI because BMI does not distinguish between muscle mass and fat mass. So there's no way to tell using BMI if the weight is associated with lean body mass, which is healthy, or fat mass, which is not healthy. This is the end of this field-based body composition section. A new video will be uploaded for the lab-based body composition. So in the previous section, we talked about why BMI or body mass index is not a good indicator of body composition, because it only takes into account body mass, and we can't differentiate if that mass is coming from fat mass or fat-free mass. So in this section, we're going to cover different methods of assessing body composition. There are different compartment models that can be used. In this section, we're only going to talk about that two-compartment model, where we're going to be able to break down the body into either a fat mass component or fat-free mass component. There are other models out there, such as a chemical model, which would break down the body into different chemical elements. So for example, for the fat component, this would include both adipose tissue and the essential fat of the cell membranes. In the anatomical model, this breaks down the body into functional compartments. So it'll break it down into the organs, the muscles, the adipose tissue, and bone. So again, in this section, we're going to be using a two-compartment model where we're going to assume the body is going to be broken down into fat mass and fat-free mass. There is a difference between fat-free mass and lean body mass. Fat-free mass is the mass of the body that has zero fat. Lean body mass is the mass of the body that includes the essential fat of the body, for example, cell membranes. So be sure you're able to discern between the two fat mass, the fat-free mass, and the lean body mass definitions. Again, lean body mass includes essential mass or essential body fat, and the fat-free mass contains zero fat. There are assumptions of this two-compartment model, one being that the densities of fat and the fat-free mass components are additive and the same in everyone. We know that this is not true. For example, in African Americans, we know that their bone density is denser than the bone density of Asians, for example. Another assumption is that the proportions of water, mineral, and protein in fat-free mass are constant within and between individuals, which we also know there are ethnic and racial differences. And each tissue type represents a constant proportion of fat-free mass. In this section, we're going to examine hydrostatic weighing or underwater weighing, which is the gold standard, and air plethysmography. These two methods use density in its methodology. So the first method we're going to talk about is the underwater weighing or hydrostatic weighing. This is based upon Archimedes' principle. Archimedes was a Greek mathematician who was asked by his cousin, King Hero, to determine if the goldsmith had cheated him out of gold. King Hero had asked the goldsmith to create a laurel leaf crown out of gold. When he heard rumors that the goldsmith may have replaced some of the gold with a cheaper metal, he was furious, and so he asked his cousin Archimedes to determine if the crown was pure gold. So presented with this problem, Archimedes thought about how to solve this problem. When he entered the bathtub, this is how the story goes. When he entered the bathtub, the water spilled out over the sides because his body had displaced the water. And then he realized he found the solution and he shouted, "Eureka, Eureka." He knew that density is equal to mass divided by volume because he was a Greek mathematician. So if we could determine density by taking the mass of the crown and dividing it by the volume of the crown, we could determine density. And he had discovered by displacing water, he can determine the volume of the crown. So how we apply this in densitometry and underwater weighing is that an object submerged in water is acted on a buoyant force equal to the weight of the water it displaces. So for example, we have a 5-kilogram weight that was measured in air or on land, and then we submerge it underwater, and now we can see that the weight is 3 kilograms. The water that was displaced by submerging the weight was 2 kilograms, which essentially is 2 liters of water. So you'll notice that the difference between 5 and 3 is 2. So the volume of this weight is 2 liters. And we determine this by taking the difference of the mass in air and subtract the mass underwater. So when we apply this to our body, we're able to determine our body density. We use the equation density is equal to mass divided by volume. So we know our body mass on land. We can measure that with a scale. And then we use the underwater weight to determine body volume. This is the equation that is given to you on your lab worksheet, where the body density, abbreviated dB, is equal to the mass of the body on land divided by the body volume, which is this entire denominator here. So the mass in air minus the mass of water is your volume, but we need to account for the density of water. The density of water is going to be dependent upon the temperature. So this chart shows you the relationship between water temperature and density, where the higher the temperature, the lower the density. So in water that is 80 degrees Fahrenheit or 26.7 degrees Celsius, this corresponds with a density of 0.98 grams per cubic centimeter. We also need to take into account residual volume and the GI tract volume, or the gastrointestinal tract. Remember, when we exhale all of our air, we still have some air left in our lungs, and this is what we call residual volume. Residual volume is based upon the person's age, height, gender, and smoking status. We have a chart that we will use in lab to estimate the person's residual volume based upon their age and height. And then for the GI tract, for adults, we assume it's 100 mLs. So if we're able to determine the person's mass underwater, the other variables in this equation are known, and then we can solve for body density. Once we get body density, we will plug them into a body fat equation, and this is called the Siri equation. There are many equations out there that can be used. This equation was derived from Caucasians. So if your subject is Caucasian, it makes sense to use this equation. Your ACSM guidelines to exercise prescription and exercise book on page 78, table 4.3, will give you a list of equations that are going to be specific to your subject of different ethnicities. And you'll find that the Filipino and Hispanic ethnicities are underrepresented in that section. Just because the way those equations are derived are from testing people of that same ethnicity across an age range, and you have to have a certain number of subjects per age. So if that demographic is not available to the researcher, then developing these equations is not possible. So we're going to take an example of Craig and Brad. They are both the same height. They both weigh the same on land, but their mass underwater is different, where Craig is 5 kilograms underwater and Brad is 3.5 kilograms underwater. From this, we can determine that Craig is denser because he's heavier underwater, which we would assume correctly that his body fat would be lower because fat is buoyant, and the fact that he's heavier underwater suggests that he has more muscle mass or lean body mass. To determine their body volume, remember, we're going to just take their mass on land and subtract their underwater weight. And so the volume of Craig is 88 liters. And then for Brad, it's 89.5 liters, where we took 93 minus 3.5. So if we were to take these data and plug and chug, we would confirm that Craig indeed does have a higher body density of 1.0485, whereas Brad has a body density of 1.0307 kilograms per liter. So Craig is denser, meaning he has less body fat. When you guys do these equations in lab, do not round off your numbers because you notice that we carried out the numbers as far as we could. So do not round it off because it would result in inaccurate body fat numbers. Okay, so once we have the body density, now we can plug it into the percentage of body fat equation. So who has a larger body density? Craig does. So who would have more percentage of body fat? Brad would. Okay, so now we can plug into the Siri equation. We're assuming they're both Caucasian and they're male, so we're going to use the appropriate equation. And we can conclude that Craig has a percentage of body fat of 22.1 and Brad has 30.2% body fat. So since we're using the two-compartment model, we can now determine how much of their body mass is fat mass or fat-free mass. And all we're going to do is multiply their fat percentage by their mass. So Brad's fat mass is 28.1 kilograms, and his fat-free mass would just be his body weight and subtract out his fat mass. So you can see how the two-compartment model is applied, where we take the percentage of body fat, multiply it by their body weight, and that absolute weight or mass represents their fat mass. And when you take this mass and you subtract it from their entire body weight, you would determine their fat-free mass. And I just found that this is a typo here. So this should be 20.6 kilograms in this blank. Okay, so the residual volume is the largest contributor to error. Also, the technical error in the sense that the subject would have to expel all their air possible, because not expelling all of their air would make them more buoyant, make their underwater weight lighter, and make them look fatter than they really are. Also, this age, sex, and race affects the density of the fat-free mass. So being sure to also use the correct equation would help. Use the correct body fat equation would help. The guidelines for hydrostatic weighing would be not to eat 4 hours prior to testing. Of course, to avoid eating gaseous foods, which will make you more buoyant. We would calibrate the scales, which you'll see in a video that I will upload into the lab section. And we would want to get 2 underwater weights within 100 grams of each other. Ideally, would measure residual volume, but in this lab, we do estimate it with that chart dependent upon the subject's height and age. Weigh females outside the perceived peak body weight during their menstrual cycle, and carry the body density value out to 5 decimal places. Do not round any number. So the next method is the BOD-POD, or air plethysmography. It's similar to the underwater weighing technique, where instead of using water, in this case, we're going to use air to determine body volume. So the volume is measured by air displacement from this person sitting in the BOD-POD. And this also has the same assumptions of the two-compartment model. So the reason why the person must wear a swimsuit and swim cap is because of the pressure changes, or the volume changes as a result of temperature of the air. So if you think of a person sitting in the BOD-POD, the air that is closest to their skin is going to be warmer than the air that is furthest from them. The air that is closest to them is going to be warm, which is going to make it more compressible. And this is going to alter the machine's calculation of the person's body volume. So likewise, wearing bulky clothing would trap air close to the skin and make that air close to the skin more compressible, and it would underestimate the person's body volume. If you underestimate the person's body volume, it would increase the density of that person. So this is the reason why they need to wear a swimsuit. Ideally not have any facial hair, because facial hair will underestimate percentage of body fat by about 8%, which is negligible. And wear a swim cap to keep the hair closest to the scalp, because we don't want to increase the amount of compressible air around the head. So to explain this a little bit more. So if we know that the density is equal to mass divided by volume. So if we decrease volume with the bulky clothing, right? So if we wear bulky clothing, the air around the skin is going to become more compressible, and it's going to underestimate the person's body volume. As a result, as this denominator gets smaller and smaller, what's going to happen to density? It's going to increase density. And as we increase density, what would happen to body fat? It would underestimate body fat, right? Because the more dense you are, the less body fat you have. So this is why the subject must wear a swimsuit and a swim cap, and ideally not have facial hair. So the bod pod works when the person sits in the front chamber, and there is a diaphragm which oscillates that creates small volume changes opposite in direction. And using the bod pod, we're able to determine the person's body volume. So unlike the underwater weighing, where we ask the subject to completely submerge themselves and exhale all of their air, the person in the bod pod just sits, and we need to estimate their thoracic gas volume. So the thoracic gas volume is similar to underwater weighings, residual volume, and GI tract volume. So like underwater weighing, which you will see, how we calibrate it in the video, the bod pod is also calibrated against a known volume. And in this case, it's a 50-liter calibration cylinder. At least 2 measurements are going to be taken, and they need to result in 150 ml volume within the 2 measurements. And it just requires a subject to sit still for 20 seconds. So when working with a population that is uncomfortable underwater, or for example, may be too buoyant to be weighed underwater, the bod pod would be a good alternative. So the 2-compartment model may underestimate body fat by about 1.8 to 2.8% when compared to a 4-compartment model. It is as accurate and valid as underwater weighing, but the underwater weighing is still considered the gold standard. And the bod pod has good reliability and low technical error, because we don't ask the subject to expel all of the air, and it's just the subject sitting in the bod pod. So this is the end of this section, and I will upload another video for the other body composition methods. This is the body composition section, chapter 15. Before we get into the material, I want to show you obesity maps put out by the CDC, the Centers for Disease Control. This data is based upon the BRFSS, the Behavioral Risk Factor Surveillance System, and it's showing you the states and the rate of obesity. So in the states with the dark blue, they have 10 to 14% of the population is obese. And in the lighter blue, less than 10% of the population is obese. So this is data from 1985, and I'm just going to scroll through. And this is 1986, 87, 88, 89, 90. 91, a new category was added where 15 to 19% of the population is obese. 92, 93, 94, 95, 96, 97, 98. Notice a new category was added with greater than 20% of the population was obese. 99, 2000, 2001, 2002, 2003. We've added a new category here. Greater than 25% of the population is obese. 2004, 2005, a new category was added where greater than 30% of the population was obese. 2006, 2007, 2008, 2009, and 2010. So this is the last map that the CDC has put out. However, they have other maps available for different ethnic or different races. And this is data from 2016 to 2018 showing the obesity rates of non-Hispanic white adults. And notice here there is a new category where greater than 35% of the population is obese. So you can see why the topic of body composition is very important and relevant today. So this is the end of this video, and I will start the PowerPoint slides in a new video. In this section, we're going to cover field-based methods for measuring body composition, primarily skin fold measurements and BIA, or bioelectric impedance analysis. For the skin fold technique, you'll need a caliper, and the general idea is to use the specific sites that are outlined in the ACSM guidelines book and pinch the skin so that you're able to lift the subcutaneous tissue and fold the skin upon itself and lift it away from the underlying tissue, and then use the caliper to measure the thickness of the skin. This is done in a rotational order. For triceps, for the 3-site model, it's triceps, suprailiac, and thigh. And for the chest, for the males, their sites that we would measure for this 3-site equation would be chest, abdomen, and thigh. All of the measurements are typically done on the right-hand side of the body, unless there is something, unless the subject's right-hand side of the body does not accurately reflect their entire body. For example, if they were immobilized due to an injury and so their leg was in a cast or their arm was in a cast. In this case, taking the measurements on the right side of the body would not be a true representation of their body composition. So in this case, it would be appropriate to take measurements on the left-hand side of the body. Like all of the methods that we've gone through, there are assumptions of the skin fold method. One of the major assumptions is that the distribution of fat subcutaneously and viscerally is going to be the same for all individuals. We know that this is not true because older individuals have less subcutaneous fat than younger individuals. Also, we know that Japanese Asians have a higher percentage of visceral fat compared to subcutaneous fat. So when you look at somebody from Asia, they may appear to be lean, but once you do underwater weighing or the bod pod, where body density is taken into account, you will see that the proportion of visceral fat is higher than the proportion of subcutaneous fat. So their body fat percentage might be a little bit higher than what you would have hypothesized just by looking at them. Also, another assumption is that there's a relationship between subcutaneous fat and total body fat, and therefore the sum of several different skin fold measures can be used to estimate total fat. And then the relationship between the sum of skin folds and body density is linear. So skin fold measurements have technical sources of error where the person doing the measurement will introduce variability in the measurement. Typically, the abdomen and thigh have the highest percentage of variability. Also, you want to make sure that the participant did not exercise immediately prior, because remember the intracellular, remember the fluid shift into the interstitial space, making that area edemic. So it would overestimate the skin folds and thereby overestimating the person's body fat. There are different types of calipers out there, one being the Harpenden. The Harpenden is the most accurate skin fold caliper that is made. It costs about $400. The Harpenden produces smaller values than the line caliper, and the equations in the ACSM book correspond with the line caliper. So if you were in lab, you would be able to try both the Harpenden and the Lang, and you will notice that the Harpenden, or this caliper, exerts more pressure upon the jaws when it's let go, when this handle is let go. This is the Lang caliper, and it costs about $175. The reason why the Harpenden or Lang caliper are used in research is because regardless of how open this jaw is, it's going to exert the same amount of pressure regardless of the jaw openness. So to measure skin folds, you would use either the Harpenden or Lang caliper and measure the skin fold thickness using the different sites. So in lab, we would typically use a 3-site formula. So in males, it would be chest, abdomen, and thigh. In women, it'd be triceps, suprailiac, and thigh. If we were going to use a 7-site formula, notice that the sites are exactly the same for men, or for males and females. When using these different sites in research, I found that the 3-site formula does not or the 7-site formula does not provide more accurate results. So this is why in lab we ask you to do the 3-site formula, because it's just as accurate as the 7-site formula. I also wanted to point out that when you take the sum of the 7 skin folds or the 3 skin folds, this is the sum of each skin fold that you have taken. And so for this body density, this equation continues onto the next line. So this is one very, very long equation, and this is the subject's age. And notice that this is the sum of 3 skin folds squared. So when you're doing these equations for lab, make sure that you either use a graphing calculator or use Excel for the calculations. Once you get the body density, then you would plug it into the appropriate equation to get percentage of body fat. And this table is taken from the ACSM guidelines for exercise and exercise prescription book. So you'll notice that the white or Caucasian, age 20 to 80, this was the Siri equation which was presented in class. And then once you get the percentage of body fat, you would compare it against the normative tables. And for college age students, ages 20 to 29, you would use this column. And you'll notice that as we age, our normative tables become more lenient. So be sure when you're doing this in lab that you use the right column according to the person's age and sex, so male and female. The next method that we're going to talk about is bioelectrical impedance. Impedance, abbreviated by the capital Z, is the opposition to flow of current. Basically, what BIA is, or bioelectrical impedance, is that this machine is going to send an undetectable electrical current through your body. And the faster the current travels from one side to the other side of the body, the more water you have. The greater water component you have, this equates to greater skeletal muscle mass. So basically, this is the premise of BIA. The assumption of the BIA model assumes that our body is a perfect cylinder. So we're assuming that this person is a cylinder and the movement of the electricity from maybe foot to hand is moving across a cylinder-shaped body. This is the traditional BIA method where you'll have the subject lay supine for 5 to 10 minutes prior to taking the measurement. You want them to lay supine so that their fluid shifts reach a point of homeostasis, because as we lay down, now our heart and body are not working against gravity, and then the water will then be redistributed up into the upper torso, and blood will no longer be pulled down into the legs or the feet. Then you would attach electrodes to the individual, and then this machine would send an undetectable electrical current that you cannot feel through the body and give you the percent body fat based upon the speed of that current. This BIA model has been commercialized, and you've seen these as the Tanita scale at the store and the handheld Omron. The Tanita scale is the one that you stand on these metal plates, and it sends an undetectable electrical current up the foot, through the foot of one leg and down the other leg. So it basically takes or estimates a percentage of body fat in your lower half of the body. On the other hand, the Omron, the handheld device, which sends an electrical current from one hand to the other, takes a percentage or estimates the percentage of body fat in your upper body. I found that the Omron is a pretty accurate method of measuring percentage of body fat, and it's relatively inexpensive. I believe you can find it online for $50. So this is a really good option if you want to measure percentage of body fat in the field, is using this Omron. There's something else called a segmental BIA model. And remember I said that this BIA assumes that we're one cylinder. The segmental BIA model breaks up the body into 5 segments, where each segment represents the limb, the leg, or the trunk. So there's 5 segments that the body is broken up into. And this is important when we want to measure any fluid shifts from limb to limb. So say a patient has abnormal fluid distribution and we want to monitor their lymphedema symptoms over time. This is an example of when this segmental BIA model would be appropriate. So in this model, the subject will stand on 2 metal foot electrodes and then hold on to 2 handles. And this model will send 2 types of frequency, a low frequency and a higher frequency. The low frequency will pass through the extracellular water or the extracellular space through the extracellular water, and the higher frequency will pass actually through the cells. So through both the intracellular water, the water contained within the cells, and the water surrounding the cells, or the extracellular water. So this model is really good for special populations, for patients with cachexia who have abnormal amounts of percentage of body fat because they're unable to keep on body weight and they are having a hard time keeping on skeletal muscle mass and so forth. So we use this BIA method, the segmental BIA method, in the clinic, and I've found so far, based upon comparing this method to the handheld Omron, that the measurements are pretty close. I would say plus and minus 2% body fat, which is pretty darn close because this piece of equipment costs $50. And depending on which model you get for this in-body, it can cost upwards of $20,000. So the handheld Omron I found has been a trusty source and a trusty way of measuring percentage of body fat. Of course, we're relying on the speed of the electrical activity based upon water component. So this means there are assumptions that we need to take into account. For example, we're going to assume that your subject is hydrated. We're going to assume that the person did not previously just exercise, which would cause fluid shifts into the interstitial space, which would make their body fat look lower than it really is. We're going to assume that they're fully hydrated and they are not dehydrated. For example, they didn't drink a lot of caffeine or another diuretic such as alcohol. Since this method measures the speed at which this undetectable electrical current moves through our body, it doesn't take into account the movement of the electrical current through our digestive tract, our GI tract. So this means that if you eat or ingest something immediately prior to doing this method, it will have a minimal effect. However, if you've eaten or drank a lot 2 to 4 hours prior to doing this method, it would affect the resistance and impedance because whatever you've ingested would have been absorbed from your GI tract. So this is what this bullet point is saying, is that eating or drinking immediately prior to the test, so within the first hour, would have minimal effect versus measurements taken 2 to 4 hours after a meal would decrease the resistance and impedance. So of course, other things like sitting in a sauna or a jacuzzi that would cause fluid shifts and dehydration, these things would also alter the results of BIA. So guidelines include making sure that the subject has not previously exercised, because if you exercise, it will increase the blood flow and warm the skeletal muscle, which will decrease the impedance and underestimate the percentage of body fat. You want to make sure that the person is hydrated normally and did not arrive for the test dehydrated as well. Body position will also be affected. So the bottom line is you want to take the measurement under the same conditions pre and post exercise. So for the traditional BIA, when the subject is supine, you want them to lay supine for about 10 minutes prior to the test to allow those fluid shifts to normalize. If you're using the handheld Omron or the Tanita, where these tests are going to be done in the upright position, you want to make sure that this person has been standing in this upright position for at least 10 minutes. Again, so you just want to make sure that the conditions are normalized and the same for both the tests. And this concludes this section.